In last class, we have discussed about the neutron stars and pulsars. So today we are discussing about white dwarfs, then about black holes. In the case of white dwarfs, here we are considering the post-main sequence evolution. Post-main means if this is the main sequence, here post-main sequence lies. Here, white dwarfs are lying here. And here, the only energy left is the gravitational energy. Due to this gravitational energy, the star contracts repeatedly, contracts again and again. Contracts means volume decreases, pressure increases, temperature increases. So what happens? When pressure increases, the mass is accumulated at the center, so the density of star becomes very high. And this degree of contraction, this high degree of contraction, release enormous amount of gravitational energy. Due to this collapse, as I have mentioned earlier, temperature increases. So volume decreases, normally radius also decreases. And as we have mentioned earlier, the density of the interior of the star is very, very high. That is about 10 square to 10 cube gram per centimeter cube is further increased. And due to this, heavy nuclei starts degeneracy. The degeneracy starts also in heavy nuclei. And now thermal energy are radiated and stars are cooling to meet their final death. This stage of star is called a white dwarf. So you can see the figure. And here I have given two separate pictures. First one is Sirius A, which lies in the main sequence. And the second one is Sirius B, which is a white dwarf. This is in the post-main sequence region. Actually, these two are binary stars, so they are rotating each other, as in this figure. The white dwarfs are of average density in the range 10 raised to 5 to 10 raised to 6 gram per cubic centimeter. In this phase, electron gas is completely degenerate except in outer layers. At the center of every planetary nebula, there is a very tiny, hot white dwarf. As we know, it is the burned out core of the original red giant. The former form of this white dwarf is a red giant. And this white dwarf is highly rich in carbon and oxygen. And this red giant is also contains carbon and oxygen. And this is produced due to the helium burning reactions, as we have discussed earlier. Now the outer layers of the red giant is removed, no longer producing energy. And the white dwarf, they collapsed down to a very small volume. About 10% of all the stars in the galaxy may be white dwarfs, but they are so faint so that we can only see the nearest ones. The red giant puffs of the outer layers. The exposed core is seen as the bright central star in a planetary nebula, which lies on the far left of the HR diagram, as I have mentioned earlier. The core of white dwarf is very hot. It appears as a bright point of light with a temperature as high as 10 raised to 5 degrees Celsius, 1 followed by 5 zeros degrees Celsius. After that, the core cools. When core cools, it moves to the left lower corner of a chart diagram. That is the first main sequence. And finally, these white dwarfs will fade away. Its material is million times denser than water. Highly denser. The gravitational field around a white dwarf is intense. A person standing on a white dwarf would weigh about 600 tons. On Earth, it is about 60 kilograms. But if you imagine a man is standing on a white dwarf, he will weigh about 600 tons. Similarly, if you consider a matchbox of white dwarf material, it will weigh as much as an elephant on white dwarf. But one more thing, when it contracts, its radius decreases again and again, but its mass increases again and again. So radius is inversely proportional to mass. Our sun is also will become a white dwarf, but it is after billions of years from now. The white dwarfs are faint because they are so small, lacking a source of energy production. So they fade. And there is a particular limit for becoming a star to a white dwarf. That particular limit is 1.4 times the mass of our sun. All stars below a mass equal to 1.4 times that of our sun will become a white dwarf. And this particular limit is called Chandrasekhar limit. And most of the interior of a white dwarf is degenerate and isothermal. And the pressure energy is given by the equation 8 pi me raised to 4 divided by 3h cube c5 f of x. This f of x is a function. It can be defined as the equation given in the PowerPoint. F of x is equal to 1.1 by 8 x 2x square minus 3 into x square plus 1 raised to half plus 3 sin h inverse x. This is the value of f of x. And f of x is a function of x. X is equal to P0 by MEC, where P0 is the threshold momentum. The density of the electron gas is given by equation 2, rho E equal to 8 pi mh by 3h cube, me cube, c cube, chi cube, mu E, where mu E is equal to, mu E can be defined as 1 by mu E equal x plus half y plus half z, where x is the fraction of hydrogen, y is the fraction of helium, and z is the fraction of all other gases present in the star. Mu e is the mass in atomic weight, units per electron. Mu e is equal to 1 for hydrogen and 2 for helium. And this mu e reduces to a form 1 plus x, 1 plus half into 1 plus x. So half into 1 plus x. And the equation of state is independent of temperature. So the problems of white dwarf structure can be considered in two separate parts. First one is hydrostatic or mechanical, and second one is thermodynamic or physical. For hydrostatic and mechanical equilibrium, we have dP by dr, which is the pressure gradient, is equal to minus g rho of r mr by r square, and dmr by dr is equal to 4 pi r square rho of r. Pressure is independent of gas temperature, as we know. It depends on rho and mu e. For a given composition, mu e is fixed. Here we have to select x is equal to 0, mu e equal to 2, because hydrogen is totally depleted in white dwarf. Only helium is there. And in early 1930s, Subramanian Chandrasekhar put forward a theory. Even if the central density is infinite, the upper limit of the mass of the completely degenerate configuration cannot exceed mc, mass cannot exceed a limit which is called mc is equal to 5.75 divided by mu e square into m sun. Major part of the star is helium, so mu e equal to 2. Substituting the value of mu e equal to 2 and mu e square becomes 4. 5.75 divided by 4 will give 1.4375. So Chandrasekhar limit becomes mc equal to 1.4375 m sun, which is nearly equal to 1.4 m sun. The radius of white dwarf decreases as its mass increases. For white dwarfs of masses around that of sun, the radius is about 1% of the solar radius. According to Chandrasekhar, no white dwarf can have a mass greater than 1.4 times the mass of sun. So the maximum mass possible for a star which is converting to white dwarf is 1.4 times that of the mass of sun. According to Subramanian Chandrasekhar, if more massive a white dwarf is, the more it is crushed under its own gravity, and the smaller it is. More massive means less denser. As we know, mass is inversely proportional to radius. There are some corrections for the theory of Chandrasekhar limit. First, it is due to a little change that takes place in the number of quantum mechanical states which may be occupied by the electrons. This is due to the charge separation created in the electric field setup in the degenerate gas. The electrostatic field changes the number of quantum mechanical states. The second correction is due to high density. At extreme high densities, for example, rho equal to 10 raised to 8 gram per centimeter cube, some electrons may be forced onto the nuclei. This increases the value of mu e. In that case, mu e is not equal to 2. And when the above two corrections are applied, mass mc will be reduced. And this 1.4 m sun becomes about 1.2 ems. If the star is heavier than this mass, the star turns into a neutron star. And we can give some examples for white dwarfs. Sirius A and Sirius B are twin stars, binary stars. In this group, Sirius B is a white dwarf. Another example is 40 Eri B. Another example is Procyon B. We know the binary stars are Procyon A and Procyon B. Procyon A belongs to main sequence and Procyon B belongs to the post-main sequence, that is in the group of white dwarfs. The masses of above 3 stars, for example, the mass of Sirius B is 0.45 M Sun, 0.45 times that of M Sun. And for 40 Eri B, the star, white dwarf, it is having a mass of 1.1 times that of Sun's mass. Third one, Procyon B, it is having a mass only 0.6 times that of the mass of the Sun. And we can calculate the temperature of the degenerate interior and the time required for cooling of the star. The interior of white dwarf is almost isothermal. So the temperature is constant. So if you consider x is equal to 0, y equal to 0.9 and z equal to 0.1, the relation between its luminosity, mass and temperature at the transition layer at the outside interior becomes L is equal to 2 into 10 raised 6 m by m sun T transition raised to 3.5. And here TTR is the transition temperature. The relation between the density and temperature at the transition layer, rho TR is equal to pi mu E mh by 3h cube into 20 me KT TR raised to 1.5. Using the above two equations 7 and 8, we can calculate the temperature and density at the transition layer of any star with a non-mass and luminosity. When internal temperature TTR is known, the cooling time for a star of mass m becomes T cool equal to 3 by 2 km TTR divided by mh mu A divided by 2.5 L. Here mu A equal to 1.44 is the mean molecular weight of nucleus. Let us see how the white dwarfs move in the HR diagram as they cool. Here x-axis temperature is decreasing, temperature is written in the decreasing order 40, 25 into 10 cube Kelvin, then 16, 10 is in the decreasing order. And on y-axis we have written luminosity L, it is also in the decreasing order. You see the main sequence here, temperature is very less, but when mass of the white dwarf increases, its temperature also increases. You can see from this figure. For example, 0.25 m sun, 0.5 m sun, and 1 m sun. 3 examples are given in this figure. During cooling, their radii do not change, but their temperature-linked luminosity continues to decrease with time. After a certain stage, cooling takes place, and at the cooling stage, the temperature is almost remains constant and its luminosity continues to decrease with time. And at last, it will fade away from the view of our observatories. The evolutionary tracks of white dwarfs on HR diagram are shown in figure. These are the evolutionary diagram for this white dwarf's life. Along one such line, a white dwarf will be destined to move as it cools until it radiates all its thermal energy to become an invisible black dwarf. This will be the end of the long luminous life of a white dwarf. So from this figure, from this graph, from this diagram, you can conclude the life history of the white dwarf. There is an x-axis, sun's age. Here we are taking sun as an example for white dwarf. Sun's age is taken along x-axis and luminosity is taken along y-axis. Sun's age is in the increasing order and the luminosity is also in the increasing order. So at first, sun joins the main sequence group as we know. Now the sun is in the main sequence group as we know. After 5 billion years, sun reaches here. Luminosity is always constant, almost constant. And after 10 billion years is also, the luminosity is almost constant. But after 12.1 billion years, sun will leave the main sequence stage. And its luminosity suddenly increases. Then after 12.2 billion years, sun becomes a red giant. And if the age further increases, helium flash taken place. He will take place, as we have studied in the last chapter. Helium flash takes place. After that, luminosity suddenly decreases from 1000 to 10. It decreases suddenly and it becomes a subgiant stage. Sun is a horizontal branch star here. Horizontal branch means we have studied the Hayashi track. In Hayashi track, there is a horizontal region. And sun lies in this horizontal region. Horizontal branch star. Then after that, if again age of the sun will increase, then suddenly its luminosity increases. And then it becomes constant and luminosity will vary. And here the planetary nebula is ejected from its surface. And finally, after 12.36 billion years, the sun ejects its planetary nebula and it becomes a complete white dwarf. So this will explain the life history of sun.